Quantum mechanics. Quantum mechanics is the theory which treats matter with a wave-particle duality. This theory was originally developed by Einstein, Bohr, and Schrödinger, and treats small subatomic particles like electrons according to their movement both as a wave and a particle. Because of the nature of these particles, such small particles, and the way that they move, the precise path of any of these smaller particles like electrons is indeterminate. Rather than the original Bohr model of an electron, where the electrons orbited around the nucleus like planets around the sun, quantum mechanics treats the configuration of electrons within an atom as what we refer to as an electron cloud. This electron cloud looks at the probability distribution of electrons. According to the Heisenberg uncertainty principle, we cannot know both the position and momentum of an electron at the same time. This is due to the uncertainty inherent in the nature of the particle as well as the disruption caused by measuring the particle. So we can know either the momentum of an electron or its position, but not both at the same time. This is what leads us into having to consider probabilities for the location and the momentum of an electron. We usually discuss these probability distributions in upwards of 95%. That is to say that the area around an atom where we consider looking for electrons would represent where that electron would be 95% of the time or more. This creates a shape that we look at wherein the electrons are located, and it is a combination of both the probability and the wave nature of the particle that gives the particular shape of the distribution of the electron area. Different shapes represent different energies of the electrons, and the electrons within those different regions will have different energies from each other. If one particular location closer to a nucleus will have a different energy from a location further from the nucleus. The Schrödinger equation is the mathematical representation of the probability distribution of an electron. It looks at the different locations and energies of all of the electrons within an atom, and is represented by a very complex mathematical formula. We can simplify this formula down to a standard representation which is much more commonly expressed, that takes out time and a number of other factors. And the important components of this equation are the wave function, which is this psi Greek letter, that represents the probability distribution of all the electrons, the Hamiltonian operator, and the energy operator, which work on the wave function to determine the energetics of the electrons. The Schrödinger equation predicts solutions which we refer to as quantum numbers. These different quantum numbers represent the state of the electron in question. There are 4 different values that are assigned to each electron in an atom. The n value is referred to as a principal quantum number. This represents what we call the electron shell, or the level of energy that the electron is in. The azimuthal quantum number, or L value, is the subshell. So within a shell we have a subshell that splits the shell into pieces. Each of the subshells contain a series of magnetic quantum numbers, or m sub l's, which are referred to as orbitals. And within each orbital, there are electrons, in which there are either spin-up electrons or spin-down electrons. All electrons have a single value for each of these 4 quantum numbers, and no 2 electrons can have the same 4 quantum numbers in the same atom, as we will discuss later. The principal quantum number represents the shell level, or the energy level of the electron. Each shell exists with a different energy level. The higher the n value, the higher the energy. Quantization, or the process by which electrons move in a discrete value, limits the value of the shell to an integer value, 1, 2, 3, 4, etc. And the shell numbers of the electrons correspond to the period in the periodic table. The period that an atom is in represents the highest n electron in that atom. For instance, an atom in period 1 has electrons whose highest n value will be n equals 1. In period 6, the electrons will have n electrons of 6. The azimuthal quantum number determines the subshell that an electron occupies. The subshell represents the probability distribution of the electrons around the nucleus in that particular energy level, and divides a spherical shape into equal different shapes depending on the number of electrons that are occupied within that subshell. Different numbers of orbitals exist in different subshell values. For instance, a subshell value of 0 contains 2 electrons, as we will discuss. The different L values, just like the N values, are also integer values, and they range from 0 up until N minus 1. So if my N value is 1, then the highest L value I can have is 0. If my N value is 2, the highest L value I can have is 1. If I have an N equals 2 shell, then my subshell values are 0 and 1, for instance. Magnetic quantum numbers are the different orbitals that are within a subshell. So the subshell is further divided into specific orbitals. The value of the magnetic quantum number determines what orbital an electron is in. The orbitals are occupied by either 0, 1, or 2 electrons, depending upon the particular configuration, and are represented by the m sub L values. These are also integer values like L and range from the negative value of L to the positive value of L. So for instance, if I have an L value of 2, my m sub L values range from negative 2 to positive 2, negative 2, negative 1, 0, 1, and 2. Different orbitals have different shapes. For instance, a p orbital has this rather figure 8 shape to it, whereas an s orbital has a spherical shape. Spin quantum numbers represent the behavior of a particular electron in an orbital. There are either spin up electrons or spin down electrons, and each orbital has a maximum of 1 electron of each spin. So I can have both a spin up and a spin down, but not 2 spin up electrons or 2 spin down electrons or whatever. The m sub s value, or spin quantum number, determines whether the electron is spin up or spin down. The value of this quantum number is either plus 1/2 or minus 1/2. And for each value of m sub L that I have a plus and a minus 1/2 possibility. So if I had an orbital, for instance, that had a value of n equals 2, an L value of L equals 1, and m sub L value of negative 1, then there are 2 possible electrons, one which is a plus 1/2 and one which is a minus 1/2, which would be the spin up and the spin down configurations.